Welcome to my presentation for match, flow matching for multi-view anomaly detection. In multi-view anomaly detection, anomalies are usually very rare and we do not have much data on them. That's why we train in a semi-supervised fashion. We only train on normal data. So a train split would look something like this, where we have multiple multi-view instances of some objects, in this case 5 views per object instance, and they are all normal data. During test time, we want to differentiate between normal data and anomalous data. The anomalies are usually very hard to spot, and they are not always visible in every view. Some of the approaches include reconstruction-based ones, memory-based ones, zero-shot, or also normalizing flows. They are a type of generative model which is able to perform density estimation, and there are a lot of different models like C-flow, CS-flow, DifferNet, multi-flow, and many others that use this for anomaly detection. What are some of the pros and cons of normalizing? Well, the pros are that they can, in theory, perform exact likelihood computation. So each image gets one likelihood. They can be very fast during inference. Some of the cons are that they can be unstable to train. They are very limited in their architectural designs. Usually people revert to use real NVP style architectures which restrict the expressivity of the network a lot. You can see this in this toy example where we have a 2D Gaussian 2D moon example. We embed it in higher dimensional space and try to learn this distribution in higher dimensional space. Now, for real NVP in the bottom row, it falls apart after a few dimensions, whereas flow matching is able to even perform in higher dimensions. Most of your images are very high dimension. So what exactly is flow matching? Well, it is a very simple training setup. We have noise on the left side, which is pretty much just a distribution of Gaussian noise, and we have our data distribution, which can be complex, in our case, images, which is x1. We just define an interpolation between the two, which is just a simple linear interpolation using an additional variable t for time, which goes from 0 to 1. And now, at every step along this interpolation line, we just learn to push our samples from x0 to x1 at each time step. U, in this case, is our learnable network. Very simple training loss. It is an ODE formulation which makes it invertible by design, as it's a type of continuous normalizing flow. And also, we get a free choice of architecture, any MLP, UNet, or whatever we want. So what type of architecture did we use? We used a frozen image encoder E, in our case a wide ResNet, took 3 different layers and extracted features from these features. We can also calculate our interpolations xt. Additionally, we also include embedding V for the view we're currently looking at and T for the time step along our ODE. This all gets fed into a bottleneck and MLP layers, and they get brought to the decoder D1 to D3, which then again decode these feature maps, and we can calculate our flow matching loss. Using the ODE integration backwards in time, we can go from image space to Gaussian space to measure likelihoods. So how exactly do we score these anomalies? Well, in theory, the exact likelihood would look something like this, where it's the likelihood of the Gaussian prior, so it's our sample x1 moved to x0, and also the divergence along the path that it took. Now, this divergence term is very costly. Even when estimating it roughly, it would require at least one backpropagation per ODE step. This is not feasible, so our solution is to just leave it out. Our anomaly score just becomes the negative log likelihood of the Gaussian prior. So essentially the image moved to Gaussian space. Qualitative results look great. Our model is able to segment anomalies quite well across multiple views. Quantitatively, we reach great performance on the real IAD dataset. Both segmentation and detection, we are also one of the first to benchmark the Manta Tiny dataset, where we also reach great performances. We even include extra experiments on multi-class anomalies. Some of the ablations include that leaving out the divergence is essentially free, the performance is not harmed by it, and we save a lot of computation. Also, using the simplest ODE solver available is just the sensible thing to do. The Euler method with just 5 steps is enough to reach good scores. We do not need adaptive solvers. There are more ablations in paper and appendix. So to conclude, we used a simple flow matching training formula a multi-view and multi-layer architecture. We simplified the anomaly scoring, which is likelihood based, by a lot, and we reached state-of-the-art anomaly detection performance. Meet me at the poster session at ECCV. Feel free to scan the code for papers and source code, and see you around.